Everything you need to know about BJTs and why you may have been taught them wrong. Before the invention of the transistor, electronic systems relied on vacuum tubes to amplify and switch electrical signals. They were large, fragile, power-hungry, and generated large amounts of heat. Today, billions of transistors exist inside a single microchip that fits in your pocket. But here's something most people don't realize. The way BJTs are usually explained isn't the full story. Today on Engineeringness, we're diving into everything you need to know about Bipolar Junction Transistors, or BJTs. At a circuit level, BJTs are described as current-controlled devices because the collector current is proportional to the base current. However, physically, the collector current is controlled by the base emitter voltage. Unlike a diode which contains one PN junction, a BJT consists of two coupled PN junctions, sharing a very thin central region. If you'd like a refresher on PN junctions, check out our previous semiconductor video. BJTs exist in two polarities, NPN, PNP. In this video, we'll focus primarily on the NPN transistor, since it is the most widely used configuration. How do BJTs operate? The operating principle of a BJT can be best summarized by the following statement. A small base current controls a much larger collector current. This can be shown by the current gain equation shown below. IC equals beta IB. IC is the collector current. IB is the base current. Beta is the device's DC current gain, typically 20 to 200. It tells you that a tiny base current drives a much larger collector current. This equation is very helpful for analyzing circuits, but it doesn't fully explain how the device works. We need to look at the inside of the transistor to understand how amplification really works. Now, here's the part most simplified explanations leave out. The collector current does not fundamentally depend on base current. It depends exponentially on the base emitter voltage. The true physical relationship is IC equals IS multiplied by the exponential raised to the power of VBE over VT, where IS is the saturation current and VT is the thermal voltage, approximately 26 millivolts at room temperature. This equation shows that even very small changes in base emitter voltage produce large changes in collector current. The base current exists primarily because a small fraction of injected carriers recombine inside the base. Anatomy of a transistor. Transistors usually have three pins. These are labeled E, B, and C. The emitter, E, is heavily doped, and its purpose is to inject a large concentration of charge carriers, electrons in an NPN transistor, into the base region. The base, B, is ultra-thin, usually only a few micrometers thick, lightly doped, and controls carrier flow. Because the base is so thin, most injected carriers do not recombine here. Instead, they diffuse straight across into the collector. And finally, the collector, C, is more lightly doped than the emitter and physically larger. It is designed to withstand higher reverse voltages and dissipate heat efficiently. Its role is to collect charge carriers, withstand higher voltages, and dissipate heat effectively. This asymmetric design is what makes transistor amplification possible. On the body of a transistor, you will see some numbers. This is usually the part number of the transistor, which corresponds to the manufacturer's datasheet, where we can see what the transistor is rated and any other important information. Let's dive into the internal anatomy of a BJT. In this cross-section view, you'll see the thin P-type base layer sandwiched between the N-type emitter below the N-type collector above for NPN. Those back-to-back PN junctions are what allow a small base current to control a much larger emitter-collector current. If you're enjoying this deep dive into how BJTs work, make sure you hit that subscribe button and give us a thumbs up. We've got plenty more engineering explorations to come. You can also check out our online store for engineering-themed gear and tools that help support the channel. Every purchase genuinely helps us keep making high-quality content. And if you want to take things a step further, consider becoming an Engineeringness member. You'll get early access to new videos, behind-the-scenes content showing how we animate and build these breakdowns, and access to our members-only chat rooms where we talk about all things engineering. Let's see how this works electrically. When a voltage of around 0.7 volts is applied between the base and emitter in a silicon transistor, the base emitter junction becomes forward biased. Electrons are injected from the emitter into the base region. Because the base is extremely thin, typically 95 to 99% of those electrons diffuse straight through without recombining. The collector base junction is reverse biased, which creates an electric field that sweeps these electrons into the collector. As a result, a relatively small base current, which is mostly due to recombination inside the base, enables a much larger collector current to flow. This phenomenon is known as transistor action. Now, let's see how this works in a circuit. Let's imagine a battery powering a light bulb through a simple on-off switch in a circuit. Flip the switch off and the bulb goes dark. But what if we want to automate that on-off action, say from a sensor or microcontroller, without any moving parts? That's where a BJT transistor comes in. Here's our automated switch. An NPN transistor sits in place of the mechanical switch with its emitter connected directly to ground, the load connector to the collector, and the other side of the load connected to the positive supply. Now, instead of your finger, a small base current will turn the light on. When we apply just a tiny current to the base through a resistor from our control signal, the transistor saturates. It behaves like a closed switch, letting the battery's current flow freely through collector to emitter and lighting the bulb. Remove that base current and the transistor snaps back to cut off, like opening the switch, instantly turning the bulb off. The base resistor is essential because it limits the base current and prevents excessive current from damaging the base emitter junction. Because there are no moving parts, this electric tap can flip thousands or millions of times per second, driven by anything from a microcontroller to a light sensor. Operating modes and characteristic curves, BJT. On screen is the BJT output curve. Collector current plotted against collector-emitter voltage for several base currents. You'll notice it breaks neatly into three regions. In cutoff, the base current is essentially zero, with no drive at the base. The collector current also falls to zero, just like an open switch. As you move into the active region, the emitter-base junction is forward biased, while the base collector junction stays reverse biased. Here, a small base current controls a much larger collector current. In the active region, the collector current is primarily controlled by the base emitter voltage and only weakly dependent on collector voltage due to the early effect. Finally, in saturation, both junctions are forward biased. The transistor behaves like a closed switch, allowing maximum current to flow from collector to emitter with very little voltage drop. The transition between active and saturation is not instantaneous. Charge storage in the base region limits switching speed, which is why BJTs are generally slower than MOSFETs in high-speed applications. By toggling between these regions, BJTs switch and amplify signals with precision and speed. Even today, many integrated circuits rely on BJTs at their input stages because they offer consistent performance and highly accurate signal amplification. If you enjoyed this deep dive into bipolar junction transistors, make sure to subscribe to Engineeringness, give this video a thumbs up, and share it with someone who loves real engineering. Stay curious and keep exploring the physics behind the technology that powers our world.